votre aide?
Well, yes, I think so. I'll put on to see what happens.
Is he driving? You're driving, you know?
It's disappeared.
Oh, since I sense that. So, was the food any better? I gave up on that.
Oh, I didn't go.
Oh, you didn't go to
I played squash.
סך? שלחתי לך איזה אימייל, ראית? כן. מה? לא יודע, תחשוב, אולי יש לך איזה משהו מעניין לעשות.
האנשים שאני צריך שיעשו, אני פשוט עושים.
מה?
האנשים שאני צריך שיעשו דברים פשוט עושים אותם.
לא, אבל זו הזדמנות, לא יודע, אולי זה כן יכול. זה יכול להיות משעשע. אבל זה גם, אתה יודע, זה מושך. תחשוב על זה קצת.
Okay, so since I'm the only thing standing between you and a nap, we should start. So thanks for surviving. So what I'll tell you about this afternoon is more about as a continuation of what Matt just spoke about, and we'll talk a little bit more about diffusion through choices that individuals make. So we want to understand how choices actually depend on the structure and location within a network, and in particular how a network impacts behavior and welfare, and how the relative location within the network affects these things as well. We also want to understand how behavior propagates through the network, and this is something that's very important for a variety of applications that you already saw, like marketing, epidemiology, and so on. So the first person to coin the term tipping point was a sociologist that's not very well known by the name of Grotjens, and he suggested that tipping points are something that characterizes white flight. White flight is this phenomenon in the US in the mid-20th century of individuals of European descent moving from urban areas that were more racially mixed. And the way he thought about a tipping point is a time in which a large number of individuals rapidly and dramatically change behavior. So just to give you a sense of what it looks like, this is a picture of Chicago, and this is data from the census. So what you see here is on the x-axis, the percentage of minorities or non-whites in 1970, and on the y-axis, the change in whites over the 10 years that followed. So this is basically looking at the census 10 years later. And what we see is something that looks like a tipping point, where around 5%, if you have less than that, people stay. If you have more than 5% minorities, people leave. And this is actually something that's
50%, they change the definition of what majority of minorities or not?
Sorry?
I don't understand. Above 50% minority is still minority, so it's now the blacks, correct?
Right, so I'm not sure I understand. So this is Hispanic or non-white, and you're just looking at the percent.
You don't have a minority of 60%, unless it's no longer minority.
No, it's minority, ethnic minority. So non-white.
So it's non-white, it's fixed non-white.
Yes,
okay.
yes.
Yeah. That's why
Yes, thanks.
So okay, no. So when it's 90% minority, it's the number of whites. So you have an increase in the number of whites coming in, or an increase in the.
No, so here you have the large.
I don't understand the right table.
So,
yeah, I don't understand the right table. Can you explain?
If you let me, yes. Yeah. So this is the percentage of minorities, percentage of non-whites, okay? And this is the change in whites, okay? So here you see a reduction. So when there's a high percentage of ethnic minorities or non-whites, you see more movement outside of whites. And when it's fairly homogeneous, whites stay or even increase in percentage.
Okay, so I'm still asking, when you have 95% non-whites, the number of whites goes up or down?
Down. It's minus.
Oh, I see.
That's zero.
That's a zero.
Yeah.
Okay.
Okay. right? This is actually evidence that was quite controversial till 2008, because before that, Easterly actually tried to estimate the same tipping points for different cities, and that didn't work out so well. And in fact, different cities in the US are characterized by different thresholds. And as a person who lives in Los Angeles, I'm very proud to note that our tipping point is higher than Chicago's. So,
Comparing things to Chicago.
all right. What followed was a slightly more formal description of this that Matt already showed us on Monday. And this was this example of the shapist polygons who prefer to be next to one another. And if you remember, the main idea here was that even a slight advantage of having a higher fraction of polygons of the same shape as you, being a shapist with even in a very slight manner, can lead to rather substantial segregation. And the model was very similar to this model of polygons. He actually drew it with a chessboard, but it's just the same idea. All right, so now I'm going to show you a model that followed from this, but is a bit more formal. And in this model, there will still be no networks. I'm just going to give you the benchmark of these class of models where we started from. So we are thinking about n agents. They're all connected, no network. Each one chooses an action of 0 or 1. And when they face a profile of x1 through xn, this should be a capital N, sorry, their utility is the following. So they look at the average action that is taken other than them. They have a cost of taking the action 1. And here, this is just a multiplication that normalizes the payoff to be 0 if you choose x equals to 0. Okay, so you have a cost of choosing the action 1, and your payoff depends on the fraction of the other people in the population who choose 1. Now, the cost could be privately or commonly known. As you'll soon see, we'll think about very simple heuristics of behavior. And you could also think about random thresholds for choosing the action 1 instead of thinking about random costs. So this would be equivalent. All right, so let me show you how this model is solved. So suppose that at each stage, agents best respond to the previous period's action in the population. Okay, so this is a very simple and naive heuristic of play. Then suppose that at period t, the fraction xt chose the action 1. Then at period t plus 1, if you're person I, then you're comparing the average of actions in the population, not accounting for yourself, and comparing it to the cost. If n is very large, then this left-hand side is approximately x, the fraction of individuals who choose 1. So what we get is that the transition formula is approximately xt plus 1 equals to f of xt. Recall f is the cumulative distribution of the costs. Okay? So a fixed point of this formula is an equilibrium. So now the shape of f is going to determine which equilibria are tipping points and which are not. And I'll soon give you a more formal description of what a tipping point actually means. But let's just think about the shapes here soon. Now, recall, this should be contrasted with the Bass model that Matt just showed you, because in the Bass model, we thought about an f that depended on time, and we had this S shape of adoption looking directly at a function that depended on time. Here, f is just a distribution, and I still didn't tell you about the adoption phase. Elchanan, you look confused?
So f is a distribution of the CIs, right?
F is the distribution.
Of the CIs, which is
Exactly.
It's data.
Exactly.
Data, f then is the outcome of the model.
Exactly. So here we're just looking at the probability that this happens. So this is just the cumulative of the left-hand side. Okay? Yeah.
If everyone makes an action and everyone doesn't make an action, it's an equilibrium, right?
If everyone.
Everyone makes an action, it's an equilibrium.
So even if everyone, well, it depends on the cost. But yes, here it's the costs are lower than 1. Right.
The same is true if no one makes an action.
Right, exactly. All right, so now we want to understand how the path of adoption changes over time. So let's look at a discrete approximation of so if we think about the change in the fraction of people who are adopting at time t, this is just f of xt from our transition formula, because this will be xt plus 1 minus xt. And we want to generate a figure that looks like this, or we want to understand what are the conditions for that to emerge, then we need delta of xt to essentially increase up to a certain point and decrease starting from a certain point. Okay? So now I'll do this mechanically. If we assume that f is differentiable, the derivative of this thing here is just f prime x minus 1. So this means that we get an S shape as long as the distribution function is such that the derivative is greater than 1 up to some point and lower than 1 starting from that point. So essentially, S shape in this class of models is tied with a sort of concavity on the distribution of costs. Okay? Does this make sense? All right. Okay, so far no networks, and now I want to tell you a little bit about how to embed networks in these sorts of models. So we want to understand how the location affects diffusion, which will tie back to this adoption of the miracle antibiotics that was introduced in the 50s that Matt told us about. All right, so let me give you a sense of how we should model these things. So let's assume we wanted to model this with complete information of the network, where we know everything. So let me show you what are some challenges that might emerge. So let's think of a very silly game where you gain 1 if anyone in your neighborhood experiments, and 0 otherwise, but experimentation is costly. So let's assume the cost of experimentation are less than 1. So you can think of adoptions of new grains, like the hybrid corn that Grillicus was studying, adoption of new software, etc. So if you're alone in the world, you want to experiment, but if you have many people around you who are already experimenting, you don't want to experiment. You want a free ride on them. Okay? So if you know everything about the network structure, let's think about the star network. So this would be an equilibrium. The center of the star doesn't experiment, and then all of the other nodes are experimenting. And this is a symmetric equilibrium, right? Everyone of the same degree is doing the same thing. Unfortunately, there's another one. So there's also an equilibrium in which the center experiments and everyone else is free riding on the center. This is a more efficient equilibrium because only one person is exerting the cost, but they're both equilibria.
Sorry, you're saying supposing you gain 1, if anyone, you mean you gain 1 if anybody told you you're on linked?
Yes,
You
yes.
didn't say that.
Oh, sorry. Yes,
Yeah,
anyone
so
who you are linked to. Yes, very good. Yes. Yes.
Neighbor.
Yes, and here everyone has a neighbor, so yes. Okay? All right, so this is a problem because we have here multiplicity of equilibria, even when we restricted things to symmetric equilibria that are pure, that are very nice, and they exhibit, in fact, very different comparative statics because here lower degrees are more likely to experiment, here the opposite happens. Now let's think what happens if you don't know the structure of the network. So suppose that we look at a very simple network, the simplest we can think of, one which corresponds to the Erdős-Renyi or Poisson network. So suppose that there is a probability P of a link between any two individuals. And let's think about symmetric equilibria. So people of the same degree do the same thing. So essentially you know your own degree. That's all you know. Then the probability that a neighbor experiments is independent of your own degree because everything here is independent, at least if we assume that the network is large enough. Okay? So higher degrees are less willing to choose 1. Why is that? Well, if fixing the probability that any random neighbor chooses to experiment, if I'm of a higher degree, the expected number of people who are next to me or are going to experiment is higher. Yeah? So higher degrees are less willing to choose 1, and in fact we'll have a threshold equilibrium here, where low degrees experiments and higher degrees do not.
That is too fast, I'm sorry. suppose that you have a situation where odd degree experiment and even don't. Then the circular is not correct, or I'm missing
Sorry?
something.
No, they wouldn't be.
Symmetry, which I have a problem with, but that's a semi-preserved symmetry. Those of odd degree experiments, those of even degree don't. Then how do you get the probability?
So they.
Independent of own degree?
So what I'm claiming is it's not going to be a symmetric equilibrium, because and the reason.
So can you go over the argument again?
Yes. So think about a person of degree D. Okay. So there is a certain probability that their neighbors will at least one of their neighbors contributes. Okay. At least one of D contributes. So if we look at D plus 1, the probability that at least one contributes is higher, right? Because the probability of contribution here is independent of your own degree. Okay? All right?
You're assuming that the distribution of degrees of my neighbors
is
independent of my degree.
Yes, I am. And this is quite kosher when the network is large enough.
Okay, but because it's Poisson, okay.
So I'm assuming that the population is sufficiently large. You had a question?
So you know how many people you know, and you know, but you don't know how many people they know.
Exactly. I just know the underlying distribution. Sorry?
And then they're independent of your degree.
Exactly. So I know everything about the underlying distribution, but I only know my private information is my own degree. Yes? Okay. All right. So there is a strong dependence on the probability of links here. So if p equals to 0, this basically means that each node is an isolated node. Then everyone is choosing one. Everyone will experiment. If p equals to 1, you can calculate the probability of contributing, and it's this little monster. And you see that as the population becomes very large, this in fact approaches 0. So everyone is connected to everyone. In fact, if we allowed for asymmetric equilibria, we would have one person contributing in pure strategies. All right, so the general message from this is, first of all, it makes it much easier to think about incomplete information here. In fact, it has much more regular patterns. So information really matters for the outcomes of the game here, or what we deduce. Location really matters, and what we saw is that there's monotonicity with respect to degrees regarding both behavior and in fact also payoffs. And network structure matters. So adding links affects behavior monotonically. And I didn't tell you anything about heterogeneity, because here changing the variance of degrees is tied with the number of links, so it wouldn't be a very fair exercise to do. So this is a very special example, but it will tie directly into the more general setup that I'll now show you and explain a little bit while I'll focus mostly on incomplete information. But are there any questions up to now? All right, Sergio?
Sergio usually saves his questions to the end.
Oh, great. Okay.
I
noticed, yeah. Okay, so the challenge, like I said, is the complexity of networks. So if we want to study diffusion, we need a way to overcome this complexity of this humongous object. And we want to find a tractable way to study behavior outside of very simple and boring networks. All right, so we'll focus on the key characteristics, and like I said, I'll focus mostly on random networks, in fact. So I'll describe to you a degree distribution, and then we'll want to understand how connected the network is. So this can be assessed by the average degree, or we can think about first-order stochastic dominance shifts of the degree distributions. And we'll want to think about how links are distributed across agents. So this relates to increasing or decreasing heterogeneity in terms of the degrees of individuals. All right, so this is the more general setup that I'll spend most of the time on. And this falls under the general rubric of network games that Jan was mentioning also this morning. So it's going to be a very special case because I'm going to focus on games that have binary actions. So the actions are either 0 or 1. Action 0 will normalize the payoff from action 0 to be 0. Action 1 entails payoffs that depend on what everyone in your neighborhood is doing. So essentially, this will be the model of payoffs. It will be a function that depends on your degree and the fraction of neighbors that choose the action 1 minus a cost. Okay? And the cost...
Don't you want the payoff choosing 0?
So the payoff that from
Oh,
choosing
using
0...
That's
Yes.
the difference between the two payoffs.
Yes, exactly, exactly. So in that sense, it's a normalization.
And V is independent of I. I noticed you want that.
V is independent of I here.
So only CI is,
Yes,
individual.
yes, exactly. So, yes. And C we'll assume is distributed according to some cumulative distribution function H that is nicely behaved. It has no items. Okay? All right, so here are some examples that fit into this framework. So you can think about a model in which we have average, in which you care about average action. So in this case, V of dx just depends on x. So this fits, for example, a classic coordination setting where you just care about the expected value of a particular action. You can think about a situation where you care about the total number of individuals. So this might be the case if you're contemplating learning a new language, you need some partners to use a new technology, and so on. We can think about a critical mass function where the value from choosing 1 is 0 up to a certain threshold, and beyond that, it's higher. So, for example, if you're thinking whether to join a revolution, maybe you want to be sure that there are enough people joining the revolution with you. It can also be decreasing in D. So, for example, if we thought about your incentives to acquire information or to acquire some costly experimentation, the higher your degree is, the lower your incentives might be. The marginal value will be lower. Yeah. Can we do random thresholds for the individuals? So we model all the individual randomness through the cost. Global, I'm not sure that will change things dramatically. Why are you interested in that?
It reminds me of global games, that's all?
There is a big similarity in this. If you think about cases in which you'll have uniqueness here, there is some sense in which global games and these sorts of games are similar because you're essentially adding individual noise and you're managing to select an equilibrium. But I won't talk much about it. To ask me later if you're interested. Okay. All right. So like I said, I'll focus on incomplete information. So in this case, you know only your own degree, and you assume that other individuals' degrees are governed by a distribution that everyone will know. We'll assume that there is no correlation in degree. This is a pretty harsh assumption. It's okay if you think about very large networks. With very small networks, it's very hard to generate this. You could think about correlations or affiliations between degrees of neighbors, and I won't talk about this here, but if you're interested, ask me at some point. So we'll think about Bayesian-Nash equilibrium here, given the types of individuals, which are their costs, their private costs, and their degree. So our graph is randomly determined. There is a probability of any node having degree D, which is given by this small p of D. And now I'll spell out the probability distribution of degrees of neighbors. This is something you already saw. This is essentially this Franz paradox that keeps coming up. But let's just spell it out because it will be crucial for what I tell you. So the probability of a given neighbor having degree D is this function, D times little p, the underlying distribution, over the average degree in the population. Okay? Now, you've seen this already, but let me just to make sure that we're all on the same page, let me just give you a simple intuition. Think about a population where half of the nodes have degree 1 and half the nodes have degree 2. So you can think about them as each pulling out the number of arms that corresponds to their degree. And now we're thinking of matching one arbitrary arm from someone to someone random in the population. We have a higher probability of hitting the degree 2 people. In fact, we have a probability of hitting a person of degree 2 with probability of 2/3, right? So this is where this formula is coming from. All right. Okay, so like I said, the type of each individual's is their degree and their private cost. And so we can think about a strategy which is a mapping from the set of types into a decision of action 0, 1. So it's a mapping from the set of types into a possibly random choice of action 0, 1. All right, so I'll now describe the equilibrium of this game in a static sense, and then we'll shift to thinking about dynamics.
So degree and cost are independent or not?
Independent. Independent, very good. Yeah, I didn't mention that. So you adopt, if and only if, the value from choosing 1 minus the cost of choosing 1 is greater than the value of choosing 0, which we normalize to 0. So in particular, the probability that degree D types adopt is just the probability that your cost is lower than this thing, and H was the cumulative distribution function of cost. Okay, so this will capture the percent of degree D types that adopt 1 when X is the fraction of a random neighbor adopting. So now we can characterize equilibrium according as a fixed point. Right? Because if we think about the fraction of neighbors, of the probability that the random neighbor adopts, we need to think about the probability that the random neighbor has a degree D times the probability that she adopts, which is just this thing over here that we just calculated. Okay? So this corresponds to a fixed point formula. And anything that satisfies this will correspond to an equilibrium. Right? So this function on the right hand.
Again, independent between types and degrees.
Yes, between costs and degrees.
Equilibria is different
Exactly.
distribution and correlation.
Exactly.
Still, I'm talking Nash.
Exactly. So I'm making life easy. Yes. So this function that corresponds to the probability that a random neighbor chooses to the action 1 will play a very important role in our analysis. Okay, so I'll denote it by phi of x, and I'll remind you of what it is. All right, so if we assume that v is continuous, then fixed points exist. So I'm not talking about a completely uninteresting object. So this is important to make sure. And now we have the first observation. So the first observation is that in the game that I just described to you, every symmetric equilibrium, where by symmetry I mean that people of the same degree use the same strategy, it's non-decreasing in degree if the utility from choosing 1 is increasing in D. And similarly, it's non-increasing in degree if the utility of choosing 1 is decreasing in D. Okay, so this monotonicity that I showed you in the first example of the experimentation is actually a fairly general characteristic in this setup. So let me give you the intuition, and it's basically what I just told Sergio for the special example. If we think about a symmetric equilibrium, a random neighbor has a probability x of choosing 1 and probability 1 minus x of choosing 0. So if we think about an agent of degree D plus 1, when the utility is non-decreasing, this means that the payoff from 1 for a person of degree D plus 1 is at least as high as the payoff from 1 for a person of degree D. So if this person is willing to choose the action 1, so will this one for the same costs. Right? And here the fact that they're independent is important. Okay, and similarly for V, which is non-increasing. Does this make sense? Okay. All right. So now let's transition to diffusion. So we're going to contemplate a very simple variant of dynamics here. So we're going to think about starting with some x0. So some fraction of the population gets infected, some fraction of the population gets a a free iPad, what have you. And now at each point, we have a sort of myopic best response. So at each point, each individual sees the aggregate probability of a neighbor choosing the action 1 and best responds to that. So x1 is going to be this phi of x0. Xt in general will be phi of xt minus 1. So this is a very simple type of dynamics. You could interpret it, yes?
It's expectation, it's not,
Oh, you have a, yes. So this is just your best responding to what you think others will be doing, given what they did last time.
so really have in mind the continuum essentially of
Basically,
of no,
yes,
and,
yes,
okay.
exactly. So there are multiple interpretations of this. One is that we're simply examining how robust certain equilibria are. So we're thinking about the equilibrium set with incomplete information, these equilibria that we just characterized, and we want to think about stable equilibria, which are converged to if you perturb the system a little bit around one such equilibrium. A different way to think about it is a very naive diffusion process, where we're thinking about the best response dynamics and a quote-unquote large and well-mixed social networks. This is effectively these sorts of mean field approximations that Matt was talking about. Yeah.
Shouldn't they do that word in Gaussian?
Sorry?
First they start diffusion, and then they do backwards.
If there are so here, this is myopic effectively. If you wanted to think about forward-lookingness, in a sense, if you had complementarities, it wouldn't actually matter. It would everything would look very similar to what I'm showing you here. If the game is a game of substitutes, things get messed up. But I will assume forever now that they're myopic. But thinking about more strategic agents would be very interesting in these models.
But here people, they adopt the iPad, then in the next period they can unadopt it. Right?
In principle, they could.
Yeah.
In principle, they could.
So if you want to use the second interpretation, there has to be reversibility. Right?
So here they are allowed to reverse it. They're not
Right.
stuck.
But not all.
Oh, you
not-
want
not
them?
all, stories go along with reversible.
Yes,
adoption.
yes. Fair enough. Fair enough. I mean, you could give your iPad to your student.
We've seen this move in the previous talk.
Exactly.
Yeah,
That's
and-
right. You can't unsee the motivation.
Yeah, and there are models that consider this. I won't today. All right. So here are the types of figures that I'll think about. So this is this phi of x that we were just talking about, and now we'll think about fixed points of this phi. So these are points that intersect the 45-degree line. So this is just an example. Now what will we mean by tipping points? Think about this left intersection. If we perturbed a little bit the equilibrium here, if we moved a little bit to the right, we start with x0, then in the next period we're going to have x1, which is above x0. And then in the next period we're going to have x2, which is above x1, and so on, and we'll reach the following equilibrium. So in fact, in this case, we will have one equilibrium, which is a tipping point, where a small perturbation around it shifts you away from the point, and one equilibrium, which we'll call stable, where a small perturbation around it will get you back to the point. You can have many. Yes. Sorry, you can have many. Yes. In the figure, we have one. We have one of each. Yes. Okay, so I'm going to concentrate on regular environments. So these essentially mean that any intersection point is either a tipping point or a stable point. So in terms of the figure, just think about a case where there are no tangencies. In general, tipping and stable points will alternate. So we'll have one tipping point and one stable point. So this, and we may have more than those, and they'll continue alternating. And so what we want to know is how phi shifts as we change things in the network, as we change the networks in terms of adding lengths or changing their distribution. So let's think graphically what happens when we increase this function phi pointwise. So suppose we look at this phi prime, which is above phi, then notice that the tipping point here moves left and the stable points move to the right. So in fact, in general, as we increase phi pointwise, there will always, for any stable equilibrium in the original process, there will be a stable equilibrium that will be higher. Okay? And similarly for the tipping points. You need to be a little bit careful on the end. Yes, so you need to be a little bit careful at the end. Yes, yeah, because in principle you could have this one. If we shifted it up sufficiently, this one would just vanish altogether. Yes. Okay. All right. Okay, so let's think about adding links. So suppose that we think about first order stochastic dominance shift in the distribution of neighbors' degrees. Okay. So now we're putting more weight on higher degree neighbors. So if V is non-decreasing in D, then we already showed in observation 1 that there's a higher expectations of higher actions because people of higher degrees are going to choose the action 1 with greater propensity. So therefore, they'll be more likely to take the higher action. Now, formally, if V is non-decreasing in D, then this leads to a pointwise increase in phi. Because essentially, this function is increasing in D, and we're looking at the first order stochastic dominance shift of P. So we're looking at an average of an increasing function, and we know that as we create a first order stochastic dominance shift, this expectation will become larger. Okay. All right. So this will lower the tipping points and raise the stable equilibria. All right. I should note that it's really important to think about these first order stochastic dominance shifts in terms of the degrees of the neighbors rather than the underlying degrees. So in fact, this first order stochastic dominance shift in the neighbors' degrees does not necessitate a first order stochastic dominance shift in the underlying degree distribution and vice versa. All right. How about welfare? Suppose that V is non-decreasing in X. Okay, so far I only talked about monotonicity with respect to D. Now let's think about monotonicity with respect to X.
Capital P is D times small p, right?
Over the expectation of D.
Yeah, no,
Yes,
yeah.
exactly. Exactly. All right, so suppose that V is non-decreasing in X. Then a first order stochastic dominance shift in P will increase the payoffs for everyone in the corresponding stable equilibria. All the stable equilibria shift to the right, so we increase X, and that increases the payoffs for everyone. So in particular, we'll get higher welfare if we assume that we end up in a stable equilibrium here. Now, this ties to a general principle in these sorts of models where monotonicity with respect to X here, or the externalities, are important for welfare. So in general, I could write a more general model here. And in general, the complementarities really affect the behavior in these games, whereas the externalities affect welfare or payoffs. Yeah.
What is the welfare here? I'm sorry.
Welfare, sum of payoffs for everyone. Average pay.
Just some of them.
Yeah, utilitarian welfare.
And you say that this goes up, why?
Because as we create a first order stochastic dominance shift, then if we focus on stable equilibria, the X increases, right? All the stable equilibria increase. Now higher stable equilibria means higher payoffs for everyone. Everyone wants a higher X. Okay, so therefore we get higher welfare.
Provided, of course, that the equilibrium remains and you are not suddenly shifting.
Exactly. So yeah. So this. Yeah. So exactly. It's local. It's local. Or you can think about kind of the set, and this one set dominates the other. You have the set of stable equilibrium.
No,
Okay.
because you could have 2, and then you raise it, and this is the Pearson right to this one, which is much lower.
But
for
we're-
everybody.
No, but for every stable equilibrium in the new first order stochastic dominant shift, there will be a stable equilibrium above it. So in that sense, it's the set. That's what I mean by the domination of the set. But you're right, the number might
Okay,
change.
okay.
Okay. All right, we could do the same exercise with respect to raising cost. If you raise the cost, it just makes sense that you make things worse, so you make it less likely to adopt the action 1. Formally, it lowers phi pointwise, because essentially when we think about this function phi, we're just lowering this h. So this again raises the tipping points and lowers the stable equilibria. All right, how about variance of degrees? So with respect to variance of degrees, we can do the same sort of exercise, but now it's important to keep track of the convexity of the utility function and the cost function. So as it turns out, if we repeated the same sort of exercise, if P prime is a mean preserving spread of P, this will imply that phi is pointwise larger under P prime. So roughly increasing variance leads to lower tipping point and higher stable points. Why is it important why do we see here the convexity showing up? Well, when we increase, when we think about a mean preserving spread of P, then we're shifting degrees to the extremes. So we have more higher degrees and we have more lower degrees. So the more higher degrees does good things for us because these are people who are more likely to adopt given that phi is increasing. But the shift to lower degrees is bad because these are people who are now less likely to adopt. And the convexity just assures that the first overwhelms the second effect. Okay, so this is why you would expect the curvature to enter. And in fact, this would lead you to a natural comparison of the best-selling degree distributions that we saw so far. So if you fixed means and consider the power distribution, a Poisson distribution, and a regular distribution, they would be very nicely ranked in terms of their stable points and tipping points. All right. So now let's think about relating the payoff structure to the equilibria. So this ties to who we would want to target. So assume that V is very simple. It's multiplicably separable, and it's equal to V of D, some function of D times X. And now we're thinking about varying V of D, and we want to understand how to do this to increase the likelihood of adoption of 1. Okay. So if we can influence V, whom should we shift to get the equilibrium that we want? So this ties to the idea of whom should we target. Okay, so let's consider changing V of D by rearranging ordering. So essentially, we have a vector of these terms V of D, and we're thinking of how to associate each value to each degree. So notice that if the degree of neighbors is increasing, which means that the probability of probability of a neighbor being of degree D is increasing, then we want V of D to be increasing as well, because that will raise our phi. Now, this would be relevant for a uniform distribution. If we have a degree distribution such that neighbors' degrees, the probability of neighbors' degrees is decreasing, then we want V of D to be decreasing. So we want to put a high value of adoption for people who are more likely to adopt here. So for example, power distributions have this feature. So for different types of distributions, we'll want to target different types of people. This is kind of important because it goes against this idea of targeting high-degree nodes. And it essentially suggests, again, the importance of thinking about neighbors' degrees. So what you want to target is the most probable neighbors to have the highest incentives to adopt, rather than just the highest degrees. Now, this is a very particular way of thinking about targeting. In principle, I could also ask you, well, if I give you K new iPads or something reversible, K new New York Times articles, who should you give it to in the network? That's a very different question and a very difficult question to answer, as it turns out. So as it turns out, this is actually a question that's very hard from a computation perspective. But here we get a sense of whom we should target. Okay, the last thing that I'd like to tell you about is adoption across degrees. So if V is increasing in D, then we know that higher degrees adopt in higher percentages, no matter what the prevailing X says. Right? That's our observation 1. So the adoption fraction will always be higher for higher degree individuals. And in fact, the patterns over time depend on the concavity of H. So here is an example of a diffusion pattern across degrees. So this is an example that corresponds to a power distribution with degree -2, an initial seed of 0.03, so 3% of the population is seeded, and costs that are uniform between 1 through 5. And now we're looking at a very simple utility of adopting, which is D times X. So what you see here is that the higher degrees are adopting at higher rates, which is what we should expect from observation 1. And in fact, for this particular structure, they look sort of like an S-shaped adoption. So this corresponds to these types of studies that Matt showed us with respect to the adoption of tetracycline, for example, where we saw that higher degrees are more likely to adopt. All right, so to summarize here, the first thing is that location really matters. So V is increasing in D. And in particular, more connected individuals adopt earlier at higher rates and have higher expected payoffs. The structure really matters. And we saw that it relates to many features of the network. So we can think about adding links. We can think about changing cost. We can think about changing the variation of degrees, etc. And the adoption speeds vary over time, and they depend on the curvature of the functions. Okay, I expected way more questions from Sergio. So you get more nap time. Yes.
Concerning lowering the in points, have you considered about another situation that, for example, there's several components. If you add a link between components, maybe you can add fewer links, but if the effect will be bigger.
So here, you're right that if you had more information on the network, that would really help you. So here we're assuming very harsh restrictions on the network. So they're random and you don't know much about them ex ante. But maybe I'm not understanding your question.
So I'm considering about the targeting links. You talk about how to influence the picking points.
Yeah.
What I'm thinking is that maybe there's some special case that, for example, there's the different components exist.
Right.
And then if you target on the link between the different components.
Yeah. You don't. You're touching on an important point, which is why I said that this is kind of a complex problem. You don't even, so you're right that if we have, let's think about, let's start from 2 components and tell me if I'm not answering what you're saying. So in principle, if you thought about targeting one person, so let's think about a very, very simple diffusion where once I target one person, all their neighbors get infected and that's it. Okay, so that's where it ends. So you're right, if I had only one person to target, I would target the person with the highest degree. And if I had 2 people to target, I may want to choose people who are on different components. This issue is in fact difficult even with one component. So think about a situation where you have a network that looks like this. So now think about a situation where you're thinking of targeting only one person. Then you'd want to target either this person or this person because they have the highest degrees, right? Now suppose I let you target 2 people. If I let you target 2 people, you don't want to target these 2, right? You want to actually target one of these guys, say this guy, and someone of a lower degree, this guy, say. Because at this point, you're covering the entire network, right? And in fact, there's a theorem by Kleinberg, Kempe, and Tardash that shows that this problem of finding the best set of k individuals is NP-complete. And whether there are particular networks for which it's easy, I find it kind of fascinating, and I don't know the answer. Yeah.
So I want to go back to something. You're assuming independence in the behavior, independence between cost and degrees.
Yes.
Now, it'd be interesting to look at equilibria where there is even a simple, let's say 2 classes, yes? High cost and high degree to something, and high cost and low degree something else. And for low cost, I don't know. That may lead to some interesting behavior. I don't know. I have no clue what's going to happen. But I think that that's very this very homogeneous kind of behavior is I think may miss some interesting phenomena.
It might be, yeah. I haven't thought through it, so I don't have a good answer for you. But yes, it might be interesting. Yeah. Yeah.
So I think we had some assumptions to ensure that the function P is S-shaped, or it has that definition.
Yeah.
I was just wondering, like, those assumptions are kind of straight.
Let me see. I think I have them here. Yeah. So this is. So think about a very particular case. This is one case that will give us conditions for S shapes. So think about a situation where h of 0 equals to 0. So this corresponds to many of the examples I showed you, because for example, if your utility from 1 when everyone else is choosing 0 is 0, this would be satisfied. Okay? And let's assume that h is very well behaved. So it's just well behaved. So if h is concave, then it turns out that phi of x over x is decreasing. Okay? So this is kind of vague. But this would sort of correspond to something that looks like an S-shaped. Okay, am I answering? Okay, you're released. Thank you.